Hello viewers. So today we are going to discuss the motion of a charged particle in a magnetic field. So firstly we imagine that we have a uniform magnetic field like this. Cross implies that the magnetic field is acting into the plane of paper and it is a uniform magnetic field. And the magnitude of this magnetic field is B. And let us imagine that a charge is fired into this magnetic field having mass m and charge q, such that the velocity of charged particle is perpendicular to the magnetic field. So for the present case, we imagine that the charge was fired from this side, from left into the field, and the charge is at this point. At this point, say this point is any general point, suppose P, the charge is having a velocity v and the direction is along the arrow. So as we know that when a charged particle moves in a magnetic field, it experiences a force, and that force is called Lorentz force, which is given by F is equal to Q into V cross. And if we write the magnitude, then it would be QVB sin theta. Over here, velocity and magnetic field are perpendicular to each other, so theta becomes 90. And hence force is equals to QVB. So this is the force that is acting on the charged particle. And if we apply Fleming's left hand rule, then according to that, velocity of the charge is towards right hand side, magnetic field is acting into the plane of paper. So applying Fleming's left hand thumb rule, we can easily say that the force on the charged particle will act in this direction, perpendicular to the velocity and magnetic field both. Now this force is acting perpendicular to the velocity, so it can only change its direction, not its magnitude. And this affects the charge to move along a curved path. So the charge starts moving and it moves up to this point. Say this is the point, and over here the velocity is having this direction now. As the force is perpendicular to the velocity, so the magnitude will remain same, that is V. Now at this point again, it will experience the same Lorentz force, because the magnitude of velocity has not changed, magnetic field has not changed, and the angle between the velocity and magnetic field is still 90 degree. So that is why same force will act. But the direction of this force will change, and by Fleming's left hand rule we can easily see it is again in this direction. And due to this force, the charge moves again and comes to this point. So if I name this point as Q, this point as R, so it will again make this motion in such a way that the velocity will remain V and the force on the charge will be towards this direction. By Fleming's left hand rule, this can again be verified. And further, you can easily predict that the charge will cover a circular track. So clearly you can see that the force which is acting towards the center of this circle at every point is the Lorentz force, and the force which acts towards the center of the circle is called Lorentz force. Sorry, centripetal force. Right now it is the Lorentz force which is acting toward the center of the circle, so we can say that the centripetal force is equal to the Lorentz force, because it is the Lorentz force which is forcing the charged particle or compelling the charged particle to move along the circular track. So as we know that centripetal force is equal to mv square upon r, and the force which is the Lorentz force is qvb. So we can put these two like this, and this clearly implies that r equals to mv upon qb. So the charged particle will move along the circular path, and the radius of the circular path will be mv upon qb. If we write in terms of momentum, we can also express it as p upon qb. And if we wish to write it in terms of kinetic energy, we can write 2mk, k for kinetic energy, upon qb. So at times the other two expressions are also useful to solve certain problems. This is also very clear from here that r is equals to v upon q by m into b. So q by m is called specific charge. So you can say that the radius of the circle traced by the charged particle is inversely proportional to its specific charge. Now, if I wish to know how much time will it take to cover this whole circle, the charge is moving along this circular track. At every point the speed of the charge is v, and the radius of the circle is r, which we have already calculated. So we can say that the time taken to complete one round is equal to, time is equals to distance over speed. So the distance covered in one full circle is 2 pi r, and the speed is v. As proved above, r was equals to mv upon qb. So we can clearly say t is equal to 2 pi upon v into mv upon qb. So v and v cancels out, and the time period turns out to be 2 pi m upon qb. This result is a very important result, which shows that the time taken by the circle, by the charged particle to complete the circle is independent of the speed of the charged particle. So even if I double the speed, the time taken to complete the circle will remain the same. Even if we decrease the speed by 50% or 80% or 10%, the time will remain same. If we wish to know the frequency, frequency implies the number of rounds that it will complete along the circular path in 1 second. So frequency is reciprocal of time period, it would be qb upon 2 pi m. So this is our equation number 2, this is our equation number 3, and the earlier equation of radius is actually equation number 1. So we have arrived at 3 important results corresponding to this case. Now, if I wish to know the kinetic energy of the charged particle during its motion in terms of the parameters which are known to us, for example radius, magnetic field, mass, etc., then we can say that kinetic energy of any moving particle is in general given by half mv square. As we have already proved that r is equals to mv upon qb, so in place of v, I can easily substitute qbr over m whole square. And if I open the bracket and cancel out the terms, then my answer will be this. So the kinetic energy of the charged particle in the magnetic field will be given by q square b square r square by 2m. Now this equation is at times misleading, because if I ask you what would be the effect on the kinetic energy of the charged particle if magnetic field is doubled, my question is, what will be the effect on kinetic energy if magnetic field, which is B, is doubled. So the expression is seen generally by the student like that kinetic energy is directly proportional to B square. So kinetic energy will become 4 times. But this is wrong. That is why I said that the formula is slightly misleading. Actually, we are not considering the terms properly. If you see it closely, the kinetic energy is Q square B square R square upon 2m. Here the term of radius R is dependent on magnetic field. So if we are changing B, not only B is changing, the radius term will also modifies its value. So we need to again consider that R is equals to mv upon qb. So from here you can write BR is equals to mv upon q. And if I see this, then doubling the magnetic field is not going to affect the value of BR as a whole. Or you can say, if magnetic field is doubled, radius is halved. So the kinetic energy, if I consider it as Ke dash, so the magnetic field term is doubled, but the radius term is halved, divided by 2m, and the answer will remain Q square B square R square by 2. So if I ask you what will be the effect on the kinetic energy if the magnetic field is doubled, answer, magnetic field will not affect the kinetic energy of the charge. And it is quite obvious that kinetic energy of the charged particle will not be affected by magnetic field, because to change the kinetic energy, speed of the moving charge shall change. Kinetic energy in general is given by half mv square. Until and unless this speed term is getting its value changed, kinetic energy cannot change. And in the very initial step, I told you that the Lorentz force is Q into V cross B. That clearly indicates that the force developed because of the interaction with magnetic field is perpendicular to the velocity. So it can only change the direction, not the magnitude, and that is why the magnitude part will not be affected, so kinetic energy will not be affected. So in general you can say that kinetic energy of a charge moving through it will not be affected due to magnetic field, because Lorentz force is perpendicular to velocity. So to summarize, what we have studied is that when charged particle goes into a magnetic field for normal incidence, it goes into a circular path. The radius of the circular path is mv upon qb. The time period is 2 pi m upon qb. Frequency is qb upon 2 pi m. Kinetic energy is q square B square R square by 2m. The Lorentz force on the charge is Q into V cross B, and the force is perpendicular to velocity and magnetic field both, and the kinetic energy will not be affected due to interaction with magnet. So that's all in this video. Hope you liked it. Thank you.